Hello and welcome. Today I want us to look at design of timber column that is resisting an axial load and a moment. Now the question is, check the adequacy of the column 100 millimeter square with an actual height of 3.75 meter, which is restrained at both ends in position but not in direction to resist a long-term axial load of 10 kilonewton and a bending moment of 350 kilonewton millimeter. Now, the first process, as we said, you compute the slenderness ratio, which is lambda, which is given by effective height divided by radius of gyration. But we know that effective height is a function of the end condition. For this case, from the conditions given, you find it is given by 1 times the actual height, which is 1 times 3750 millimeter. Radius of gyration will be given by, because this is a square or a rectangular section, will be given by square root of b divided by 12, which is equivalent to that. And then from there, we can now substitute and get our slenderness ratio is 129.9, which is below 180. That is okay because 180 is the maximum allowed. We go to grade stresses and modulus of elasticity. Now here you'll say, like the way we read in the previous is still the same section. You go to our table and obtain the value. Now here we will incorporate bending parallel to the grain because we have a bending moment being subjected to the column. Now we can come here like we demonstrated, and now we add bending moment. The section is still the same, C16. Now we are only adding the bending moment parallel to the grain, which has a value of 5.3 Newton per millimeter squared. Then from there, we can go to modification factor. K3, we know it is a long-term load, long-term duration, so it has a value of 1. Then K7 is normally given by, we have different formula, but since our section lies from 73 to 300 millimeter, we use the formula K7 is 300 over H power 0.11. We substitute, we find a K7 of 1.128. Then K12, from what we did in the previous tutorial, by interpolation, we got a value of 0.261. Now we can go to compression and bending stresses. Now permissible compression stress is given by, like for compression stress, you only deal with duration of loading and the K12, which is 6.8 multiplied by 1.0 multiplied by 0.261, getting 1.77 Newton per millimeter square. Is the same as what you obtain in the example above. And then permissible bending stress. Now permissible bending stress, we use the value of K3 and K7, which is 5.3. Bending parallel to grain we obtain from the table, we multiply by K3 and K7. You find it is 5.98 Newton per millimeter squared. Now we have another value we call Euler critical stress, which is given by pi squared, modulus of elasticity minimum, divided by lambda squared. We can just say lambda squared because it is effective height divided by radius of gyration squared. So it's lambda squared. Now, if we substitute, you find it is the Euler critical stress is 3.39 Newton per millimeter squared. Now, we have been told that the column is restrained at both ends in position but not in direction. So we have to check the column such that now we have to substitute here where we have applied moment. We have been given, this is applied moment sigma MA is applied moment parallel to the grain. Then sigma MADM, it means permissible moment parallel, bending moment parallel to the grain, into 1 minus 1.5. This is the applied. This is applied compression stress parallel to the grain divided by the Euler critical stress multiplied by the value of K12. We have it there. Then you add to applied compression stress parallel to the grain divided by the permissible compression stress parallel to the grain. This value should be either equal or less than 1. Anything above 1, it means the test has failed. Thank you very much. I'm giving you this last section. Kindly compute and give the value in the comment section to check if this column will pass the test or not. Thank you. See you next time.